So welcome back to Module 5. This is week 5 of our Graduate Statistics course in the University of Cincinnati. On the previous video, we finished up with a demonstration of a random experiment. We used cards to play around and create random conditions to get a feeling for what kind of variation we can expect when we're randomly organizing the promoted and not promoted decisions in two piles. And we found a difference of 12.5%, even though they're being randomly placed in the two piles, and the number of black cards and red cards should have been the same in both piles. They weren't the same. The number of black cards representing the promoted decisions the difference was about 12.5%. And we ended saying that we can't know if this is also a likely finding, right? By just running one experiment, we need to run a variety, multiple, indefinitely many random experiments to figure out what's the likelihood of finding different outcomes. Because this is, in the end, what we want to know. Is it common for me to run this random experiment and find the difference of 30%? Of course, it's not feasible to run the experiment indefinitely many times physically with cards or drawing papers from hats and stuff. But we can use computer simulation to do this little demonstration so that you understand how is it that we can get to what is likely under random conditions and to compute the probability of observing a difference of 30% or more under random conditions. And that probability is what's going to guide our inference. But let's work through the simulation. You don't need to think that you're going to have to run a simulation like this for your exam. No way. This is not how inference testing typically happens, but it is a nice way to demonstrate the logic of it that some of you said that they really wanted to understand, right? Not just point and clicking and running tests, but understanding what's behind statistical inference. So here is a demonstration to achieve that goal. All right, so here's what we're going to do. We're going to set up our hat or our Ziploc bag containing promoted and non-promoted cards, right? Either something you write promoted, non-promoted, 48 of those little papers inside, or the red and white play cards. So here's the hat. I'm putting 35 cards in there where I'm writing out the decision promoted. That's to represent the 35 managers that decided for promotion. And I'm writing out 13 cards with not promoted written on it. That's to represent the 13 managers that decided not to promote the candidate in the file. So here it is. So we have 48. Note that they are in order. I'm putting 35 promoted and 13 not promoted in the hat. Now, just to check if things went well, we created a table with the dataset hat, and we saw that it did exactly what we told it to do. 13 not promoted, 35 promoted, just like in the experiment that we described on gender bias. All right, now what did we do on the card experiment? We drew 48 cards in random order, right? And we put the first 24 in the female pile and the next 24 on the male pile. So how do we do that in the computer? Well, we are going to use the function sample. That is a function that goes inside the object hat and pulls out random cards in there, right? So we know that the object has promoted, those are the cards. So it pulls them out in random order. How many it's going to pull out, you can tell the function. That's an input. And we want it to pull the 48, but now in random order. And we want it to put the first 24 cards in the female pile and the last 24 in the male pile. That's what we're telling you to do. And we're going to assign the first action, which is the sampling of the 48 in random order, to an object called rand_draw. And we're going to put the first 24 in an object called female decisions and the other one male, to represent the male decisions about the male candidate. So note this is the output because I just printed this one so you could see. Remember, when we created the head, things were in order. But because I'm asking you to sample it in random order, now it kind of shuffled it. So I'll take the first 24 and put inside the female pile, and the last 24 put inside the male pile. Then what's step 3? Well, we're going to count how many promoted, how many non-promoted in the data set female, which is the first 24. And we're going to count how many promotions happened in the male pile, which is the last 24. And then we can compute the proportions pretty easily by using the function prop table. So we do a function of a function, so prop table of the table. So we get a little table with the proportions as well. So let's take a look at that. So we're calculating, so those things are there. If I want to take a look at these tables, you can actually write there to print them out. So you can look at the tables themselves. I think you might have it with the writings already. I don't know why I accidentally deleted them. So let's look at the tables. So in this random experiment, again, just like on the physical experiment, 19 females were promoted, 16 males were promoted, so 79% and 67% more or less. And now we're going to open up an object just to keep our summary statistics in there, the difference in there, because we're going to run this multiple times. So we just created and it's empty. It's called promotion diff. And I'm going to mark it out because I don't want to do this again, because if I hit this, I delete everything that is in there. And then I'm going to put inside of this empty container, on the first position of this container, the difference between the females promoted and the males promoted. Okay? So let's put it in there. So first one, 12.5. More females were promoted than male, 12.5% difference. So I'm multiplying by 100 to get the percent idea. All right, but we have to do this multiple times to see what's likely, right? So let's look at it. Let's do it again. Let's go back to step 2. We're going to shuffle this thing again by sampling the hat one more time and then putting the first 24 on the female pile, the next 24 on the male pile. So it's reshuffled, and we're going to click here again to see the summaries. So this time, 18 females were promoted and 17 males were promoted. So almost the same, right? So let's look at the difference. So we're not going to run this again. Oh, shoot, it saved over the other one because we need to change the number. That's okay. So let's do it again. So that's 4% difference. So now let's do one more time with filling. Let's reshuffle the 48. First 24 on the female pile, next 24 on the male pile. Now let's look at the differences again. So again, 17 and 18, except it was flipped this time. And we're going to put that on the second position of our container. So now we're looking at a negative 4%. So we saw 4%, now we saw negative 4%. So first females, 1 got more promotions randomly. Now males got more promotions randomly again. Then we can go back there and do that again, shuffle, and do the counts. And now we saw 18, 17 again. Now we're going to put it on the third position. So we're seeing some likely stuff going on here. Now let's shuffle again. And let's do this again. Now we got 20 female promoted. Now it's a difference of 5, a little bit bigger than before. So let's see. So 20% this time. So we can keep accumulating things here, but I have to remember to change the number each time so it keeps putting it in a different place instead of saving it over. But as you can see, even to do it in the computer this way, repeating the steps 2 and 3 indefinitely many times, it's like very labor intensive, and then you forget to change the number, and you don't save something you've done. So if you need to do this 1,000 times, that would be, again, very labor intensive. The good thing about computer programming is that anything that you find yourself doing repeatedly, systematically, can probably be automated. And that's what we're going to do. We're going to write our own function, right? Where it loops through steps 2 and 3 multiple times and actually does it for us. And in the end, you have like that container saved with 1,000 results that we can then plot and look at. So again, you don't need to learn how to write the function. You just have to run it for me so that we can use it. So this function is basically taking one parameter only. It's going to be called simulation. And inside, you just tell R how many times you want it to run the simulation. So here we're setting up the hat with 35 promoted cards, 13 not promoted cards. And we're telling it to replicate the experiment 1, 2, however many times you told R to repeat. We're going to set up our empty container, and then we're going to make it loop through the steps many times, from 1 to 1,000, or 1 to however many replications of the study you wish to do. So then what do we want R to do? What we just did up there. Randomly draw 48 cards from the hat, and then put the first 24 in the female pile, the last 24 in the male file, then compute the proportions, then compute the difference, and put it inside the promotion file, right? And then we keep repeating this all the way up to the number of replications you asked. So that's what this function will do. So we saved the function here, so you know the function is there and you can use it. So this is the piece that will now run and figure out how to compute the probabilities. So we're basically telling R, please run the simulation 1,000 times for us. You know, this hat simulation. So that's what it will do. Let's run the simulation for 1,000 experiments. So note what's happening. Every time it's computing a difference, right? So males got promoted 4% times, 4% more, 12.5% more, 20% more, 12.5, 21%, so on and so forth. It's hard if there is hardly, here, that's a 30%, that's a 30% again, which is sort of what we saw on the experiment, but those are pretty rare. Notice this. I mean, they show up, so it can happen, right? A difference of 30% almost can happen, but it's not very likely. We don't see many of those. Take a look. It's almost never there, right? So we ran it 1,000 times, and now we're going to learn how to look at the result of these many replications in order to compute the probability or the likelihood that that we'll see a difference of 30% or more. All right, so I'll see you in hopefully what will be the last video or second to last. We're almost done. Hang in there.